probably, I would say, something you haven't really studied in school. You will sometime probably, for you guys in 10th grade, take chemistry. At some point in the future, you might take AP chemistry. And so this is just a little bit of an introduction here to the basics of chemistry. So before we actually get into the periodic table and atoms and molecules and compounds, can I just talk about something that I think you probably have heard of? Physical versus chemical changes. Is that something you've learned about?
Yeah.
Okay. So what is the difference? In matter, we can have a physical change that takes place, or we could have a chemical change that takes place. So could anyone tell me kind of the difference between those two? Ellie?
So a physical change is something that happens to the object where it changes the way it was in a way, and a chemical change is how it changes the way that something was. If you had something that rusted overnight, you changes the chemical matter of it.
Okay. I think you're getting there. You kind of said the same thing twice, but you saved yourself there at the end. So yes, a physical change is a change in the properties of a substance, but it's actually just still the same substance. It hasn't changed into a new type of substance. So if you took a glass and it broke, that would be a physical change. It's still glass. You haven't changed the chemical nature of that substance. What about this? If you take an ice cube and melt it, is that a physical or chemical change?
Physical.
I hear both. Who's confident in their answer to this question? Is it a physical or chemical change? And Ashley? Why?
Like it's not anything chemical changing, it's just expanding.
What is this made out of?
Water.
What is this made out of?
Water.
What if I boil it?
Water.
It's all water. So we're not creating any new substances. We're changing it to what we call state of matter. So melting anything, freezing anything, evaporating something, condensing something, those are all examples of physical change. When we have a chemical change, we're actually forming a new substance. What we end up with is different from what we started with. And Ali said iron rusting. That's a good example. When you have iron and it rusts, the rust is actually a new compound, different from the iron that was present before. There's been a chemical change. Atoms have been rearranged to form a new substance. When you burn anything, that is a chemical change. You're actually changing the molecules, changing the compounds that make up, so let's say a piece of wood. If you burn it, you're transforming it into carbon dioxide and carbon monoxide and water and other things. So you're actually changing it into a new substance. So to understand if it's been a physical or chemical change, there's certain clues that can tell you. If it is a change in phase, that is a physical change. We mean solid, liquid, or gas. If we take some salt and pour it in some water and it disappears, that's really just a physical change. Is that salt still salt when you put it in the water? Yeah. It's still, even though it seems to disappear, it's still in there. You could taste it. A change in the size of an object is a physical change. Clues that we have a chemical change or a chemical reaction, there's a change in color. Bubbles form. Smoke is released. Those are indications there's been a chemical change. Chuck?
Would there always be a change in color?
Not always, but often.
If you boil something, bubbles come out.
Yeah, that's a good question. those bubbles are just pockets of water vapor. So yeah, there are bubbles formed when boiling, but that's more as a result of what we call convection rather than a chemical. Good question. So let's do this little checkbox. You tell me what you think. Zainab, burning paper. Which one are you going to say?
Physical?
Actually, any burning something is chemical. How about crushing a soda can, Nate?
Physical.
That is a physical change. How about lighting magnesium? That means like burning magnesium. Lily?
Chemical.
That is a chemical change. Has anyone mixed vinegar and baking soda before? No? Do it at home next time you go.
Yeah,
When you go home, pour a bunch of baking soda. Don't tell your parents I told you to do this. Pour a bunch of baking soda in a bowl. Add a bunch of white vinegar or red vinegar and see what happens.
Yeah.
And be surprised. Don't tell them what happens. Elizabeth, is that a physical or chemical change? That is a chemical change that will take place this afternoon when you get home.
Can I get a permission slip saying I
No,
do it?
no, I never told you to do that.
Okay.
How about snow melting? Physical. Cassia, how about fireworks going off? Chemical. How about that egg you ate for breakfast, Drew?
Physical?
Eh?
Well, chemical because after you fry it.
Yes. When you fry something, cook something, burn something, that is a chemical change. The digestion takes place after you ate that egg and it's in your stomach being digested, Sienna.
Physical?
No, that is a chemical change. Enzymes inside of your stomach are dissolving that material. Think about it, if you were to,
What?
if you were to vomit up that egg a couple hours later, is it still the same egg that you chewed up and swallowed?
No.
No, it's been digested into just that mush.
Oh, yeah, we
I wasn't going to say, you guys made me. All right, dissolving sugar in water. Jake, physical change, dissolving something. Boiling a pot of water.
We don't have that.
Colin.
Yeah, we have a different.
Oh well. Oh well. Colin, boiling a pot of water.
Physical?
That is a physical change.
Yeah, we have mixing green.
Wait, you have that?
Yeah, we have mixing. Never mind, mixing bread.
All right, don't worry about it. It's fine. All right, let's talk about some chemistry. So now we're focusing on these chemical changes. So, an atom, we asked about this, and you guys had the right definition pretty much. An atom is basically the building block of all matter. Everything around us that is matter, it's made of atoms. So your desk is made of atoms. The air we're breathing in, made of atoms. You are made of atoms. Even if your name is Adam, you're made of atoms. Atoms are made of what we call subatomic particles. Subatomic means smaller than an atom. And there are three types of subatomic particles that we are going to talk about. There are others, but we're just going to focus on these three main subatomic particles. They're called protons, neutrons, and electrons. All right, so we get into this concept of elements versus compounds, and we kind of started to talk about this when we were answering question today. What's the difference between an element and a compound? So on the chart I gave you, the periodic table of the elements, what do you think I found on that? Elements, very good. Can you find water on there?
No.
No. Can you find carbon dioxide?
Yeah. No.
Okay, you guys look for it. You tell me when you find it.
I found carbon. Yeah, that's not carbon dioxide, though. What's a carbon? Element. We get it.
Can you find ammonium on there? Not on there. I'll give you a hint. No. I'll just give you a little hint. The answer is no. So, what is on there?
Bromine.
Everything else.
Well, not quite.
Oh.
How? Or what? Exactly. So the chart you have are elements. An element is a pure substance. Is gold in here?
Yes.
What is gold made out of?
Gold.
It's just gold.
Atoms?
It's made of gold atoms, that's all. Why isn't water on here? What is it made out of? It's made of hydrogen and oxygen, so it's not a pure substance. It is a compound. It is a combination of 2 parts hydrogen to 1 part oxygen. So elements are pure substances. And all of the known elements are right in front of you on your periodic table. So how do you think we might define compounds? How?
Like, I'm trying to think of the right word.
Your hand was in the air, right?
Yeah.
Typically in school that would indicate a teacher might call your
I'm
name.
trying to think of the
And
right
then you
word.
might have a
I'm
response
trying to think of the right
prepared
word
for
to say,
them.
like to mix them together. The way that it's like, so it's the mixture between various elements and like what it forms.
All right. Michelle, you wanna?
Mixed substances that can be separated.
Okay, and a compound can be separated. Yeah, we say it's a combination of 2 or more elements bonded together with chemical bonds, such as water, carbon dioxide. So then we get to molecules. What is a molecule? So sometimes people mix this up with atoms. They're not the same thing.
Really?
Sometimes people do. It's hard to believe, but they do.
I'll do that.
All right. So what is a molecule? How can we maybe define it or explain what it is? Ali,
Kind of like an atom.
in what way?
I mean, it's small,
It is small. Molecules are small.
hard to see with the blind eye.
Let's stop there. A molecule, so what is the small, let me ask you this question. What is the smallest possible amount of silver that I could have? No.
It's a. You could have.
What would we call it? Guess it would be tiny. Nope. It would be an atom of silver. What's the smallest amount of gold I could possibly have? An atom. How about of hydrogen? How about of water? A molecule.
Oh.
Big body.
So a molecule is the smallest part of a compound that you can have.
Who said that though?
So if I have a water molecule, what is it made out of? No, it is a molecule. John?
Atoms?
It's made out of atoms. How many atoms in of what? Yeah, it's 2 hydrogen atoms bonded together with 1 oxygen atom. That makes 1 water molecule. So hydrogen and oxygen are both elements, pure substances. We find them on the periodic table. If we take 2 atoms of hydrogen, 1 atom of oxygen, they form 1 blank of the blank water. What am I going to fill in with those blanks? They form 1 molecule of the compound water. Does anyone know what hydrogen, the element, is like?
I'm just going to ask that question.
Good question. I should have asked it myself. I did. So what is hydrogen? Anyone know anything about it?
Is it on the computer? Yeah.
It is on the periodic table, it's an element. But what about its properties? Ella? It's one of the lightest elements. It is, what state of matter is it at room temperature? Do you know that? Pettis? It's a gas. It's an explosive gas, very, very flammable gas. Some hydrogen bomb. Hydrogen can be used to power vehicles. There's hydrogen fuel cell vehicles. Hydrogen was put into a giant blimp to keep it afloat. What happened to one of those blimps that's famous? It exploded, the Hindenburg. Okay, how about oxygen? What state of matter is oxygen at room temperature? It's a gas. It's also flammable. Oxygen is what's in the air that we breathe. So if we take these two sort of combustible gases and combine them, what do we get? Something very dangerous?
No.
We get water. Something we require, that we need, that we drink. Okay? So compounds have properties that are typically different from the two elements, or more than two elements, that make them up. What's the smallest amount of water I can have? A molecule of water. What if I split that molecule of water up? It's no longer water anymore. It is hydrogen and oxygen. Okay, so an atom of oxygen or an atom of gold is actually made of smaller parts. We call them subatomic particles. And there's 3 subatomic particles that we're going to talk about. And when we talk about an atom, we talk about different kind of locations within that atom. So 2 of these subatomic particles are in the core of the atom. We call that the nucleus of the atom. And the nucleus of an atom has protons. And these subatomic particles have an electrical charge with them sometimes. You can probably guess, what charge does a proton have? A positive charge. The other type of subatomic particle found in the nucleus, in the core, is called a neutron. What do you think the charge of a neutron is? Ali?
Negative.
No. Neutron, neutral, has no charge. Then we have our third subatomic particle that is outside of the nucleus, actually quite far away from it at an atomic scale. It's called an electron. Ali, what charge does it have?
Negative.
Negative.
I just have it mixed up.
I know. Now, when we typically draw like an atom in like Jimmy Neutron or we draw them kind of like this, but this is really not all that accurate. So what is this? That's the nucleus. What is this? Electrons. This is far too compact. Okay? If this were the size of the actual nucleus, you wouldn't even see these electrons. They would be nowhere on the slide. They would be nowhere even in this room. Okay? The electrons are far outside an atomic scale from that nucleus. And so, let's watch this video to help us try to comprehend sort of the scale of the nucleus and the electron, because it's pretty extreme. Yes.
You know what dihydrogen monoxide is?
Yes. All right, just watch.
You probably already know that everything is made up of little tiny things called atoms. You might even know that each atom is made up of even smaller particles called protons, neutrons, and electrons. And you've probably heard that atoms are small. But I'll bet you haven't ever thought about how small atoms really are. Well, the answer is that they are really, really, really small. So you ask, just how small are atoms? Well, to understand this, let's ask this question. How many atoms are in a grapefruit? Well, let's assume that the grapefruit is made up of only nitrogen atoms, which isn't at all true, but there are nitrogen atoms in a grapefruit. Well, to help you visualize this, let's blow up each of the atoms to the size of a blueberry. And then how big would the grapefruit have to be? It would have to be the same size of, well, actually, the Earth. That's crazy. You mean to say that if I filled the Earth with blueberries, I would have the same number of nitrogen atoms as a grapefruit? That's right. So how big's the atom? That's really small. And you know what? It gets even more crazy. Let's now look inside of each atom. That's the blueberry, right? What do you see there? In the center of the atom is something called the nucleus, which contains protons and neutrons. And on the outside, you'd see electrons. So how big is the nucleus? Well, if atoms are like blueberries in the Earth, how big would the nucleus be? You might remember the old pictures of the atom from your science class, where you saw this tiny dot on the page with an arrow pointing to the nucleus. Well, those pictures, well, they're not drawn to scale, so they're kind of wrong. So how big is the nucleus? So if you popped open the blueberry and were searching for the nucleus, you know what? It would be invisible. It's too small to see. Okay, let's blow up the atom in the blueberry to the size of a house. So imagine a ball that is as tall as a 2-story house. Let's look for the nucleus at the center of the atom. And you know what? It would just barely be visible. So to get our minds wrapped around how big the nucleus is, we need to blow up the blueberry up to the size of a football stadium. So imagine a ball the size of a football stadium, and right smack dab in the center of the atom, you would find the nucleus. And you could see it. And it would be the size of a small marble. And there's more. If I haven't blown your mind by now, let's consider the atom some more. It contains protons, neutrons, and electrons. The protons and neutrons live inside of the nucleus and contain almost all of the mass of the atom. Way on the edge are the electrons. So if an atom is like a ball the size of a football stadium, with a nucleus in the center and the electrons on the edge, what is in between the nucleus and the electrons? Surprisingly, the answer is empty space. That's right, empty. Between the nucleus and the electrons, there are vast regions of empty space. Now, technically, there are some electromagnetic fields, but in terms of stuff, matter, it is empty. Remember, this vast region of empty space is inside the blueberry, which is inside the Earth, which really are the atoms in the grapefruit. Okay, one more thing, if I can even get more bizarre. Since virtually all of the mass of an atom is in the nucleus, now there is some amount of mass in the electrons, but most of it is in the nucleus. How dense is the nucleus? Well, the answer is crazy. The density of a typical nucleus is 4 times 10 to the 17th kilogram per meter cubed. But that's hard to visualize. Okay, I'll put it in English units. 2.5 times 10 to the 16th pounds per cubic feet. Okay, that's still kind of hard to figure. Okay, here's what I want you to do. Make a box that is 1 foot by 1 foot by 1 foot. And let's go and grab all of the nuclei from a typical car. Now, cars on average weigh 2 tons. How many cars' nuclei would you have to put into the box to have your 1 foot box have the same density of the nucleus? Is it 1 car? 2? How about 100? Nope, nope, and nope. The answer is much bigger. It is 6.2 billion. That is almost equal to the number of people in the Earth. So if everyone on the Earth owned their own car, and they don't, and we put all of those cars into your box, that would be about the density of the nucleus. So I'm saying that if you took every car in the world and put it in your 1 foot box, it would have the density of 1 nucleus. Okay, let's review. The atom is really, really, really small. Think atoms in a grapefruit, like blueberries in the Earth. The nucleus is crazy small. Now look inside the blueberry and blow it up to the size of a football stadium, and now the nucleus is a marble in the middle. The atom is made up of vast regions of empty space. That's weird. The nucleus has a crazy high density. Think of putting all those cars in your 1 foot box. I think I'm tired. Ooh.
All right, so that tries to put in perspective.
My brain hurts.
Yeah. So the main point, what are atoms made of mostly? Most of the volume is empty space. Right? So the desk you are writing on right now is made mostly of empty space.
Let's find it.
Think you could like drop it through the table?
What's that?
If you guys did have can you like drop it?
Yeah, atoms could. So, but there are also these electrons, and the forces between them are what make this a solid, not just empty space. So again, if you took how many cars? 6 billion cars, and you put all of their mass in this fish tank, that would be about the density of a nucleus. So you couldn't pick up a grain of salt if its density were the density of the nucleus.
It weighs so much.
So
It's
super dense.
Yeah, I watched that part of that exact video, I'd say like during the summertime. And I didn't watch the entire thing because I was getting way too confused.
Yeah.
So I watched it.
Your brain started to watch something
Yeah,
else.
but
Just a slime video.
now that I'm in your class, I
Now you understand it all. See? This is what science can do for you.
It's like the thing is I was having a great day before this, and now I came and
Now you're just gonna be thinking
I
about
just can't
matter and atoms.
and just like
Yeah.
Well, and at least
we're
we had
bro,
a math class before this.
bro, we're space dust, bro.
All right, so I'm gonna cancel your homework for Monday.
Bro, you know what, bro?